All right, cell voltage is the potential differences between electrodes are among the most precise scientific measurements. The way I'd like to calculate the cell voltage is a little different than what Petrucci does. Let me show you what I mean here. And so if I'm trying to figure out what is the voltage of the electrochemical cell, let's say under standard conditions, then what I do is I look at the potential for the anode here. The potential for the anode, what happens at the anode? Oxidation. And so I could call this E naught of the anode, or I could call it E naught of oxidation, or I could call it E naught for the last cell that we looked at, the oxidation couple. So that would be like, for example, zinc solid goes to Zn2+. And so all these would work. And then I'd like to combine it with the cathode potential. The cathode potential is where reduction occurs. And it would be called the, for example, here, copper 2+, copper couple. And so what I'd like to do is I'd like to combine the couples here. So for example, if I have a high anode, what we call potential or voltage, and a high cathode potential, then the cell potential should be high. What Petrucci does is he does it a little differently. Petrucci does this. He does E naught of the cell is equal to the cathode reduction potential minus the anode reduction potential. And so when we think about a redox reaction, redox is reduction and oxidation. But when you look at this equation, it's reduction and reduction. And where he gets the oxidation is this negative sign here. Because that would tend to reverse this one. And so mine is a little different. I think of cell voltages as a combination of the anode potential and the cathode potential. And if both of these potentials are high, then there's a high probability of this occurring. That is a high likelihood. Whereas he likes to think of it as a difference in the potentials. I like to think of it as a combination of the potentials. And so let's look at the individual potentials here. Well, we saw that, let me erase Petrucci's here, but we saw that this one comes out to 1.103 volts. If this is 1.103 volts, that's a combination of these two potentials. And so what does that mean in terms of this? Well, if we were to try to solve this, what we have is we have two unknowns. If we have two unknowns, we need a second equation, right, to solve it, a system of equations. But it turns out there's no second equation. We have two unknowns and one equation. If we have two unknowns and one equation, we can't solve it. This x plus y equals 1.103. And so what do? Well, we could give up and say the answer cannot be determined, or we can take advantage of the fact that you cannot have oxidation without reduction and vice versa. If we take advantage of that fact, then we've seen this happen before where we had two unknowns and one equation. We saw it in the delta H of formation of HCl. In delta H of formation of HCl, we had delta H of formation of H plus and delta H of formation of Cl minus. Two unknowns, one equation. We also saw it in the entropy. In the entropy of H plus, we saw it there. We can figure out the entropy of HCl. Well, what is the entropy of H plus and what is the entropy of Cl minus? Strong electrolyte. And so we see the same problem here. So what did we do in the past? We made an assumption. We assume an arbitrary 0. Well, zinc and copper, none of those are good arbitrary zeros. We should use the same arbitrary 0 that we've been using. What's the arbitrary 0 that we've been using? Do you guys remember the arbitrary 0 we've been using? I'm sorry? No, not the simplifying assumption. The arbitrary 0. What do you think the arbitrary 0 is? Excuse me. What have we used for arbitrary zeros in the past? Let's take a look at this table. Delta H of formation, delta G of formation, S not, CP will ignore. Well, delta H of formation, delta G of formation of the elements in their standard elemental form is 0, always 0. But this is weird. H2 makes sense. It should be 0 and 0. But H plus doesn't make sense. Because H plus is our arbitrary 0. Does 1 molar H plus have an entropy of 0? No way. That was arbitrarily set because we run into this problem. 2 equations and 2 unknowns. But if H plus doesn't have an entropy of 0 0 joules per Kelvin, that is terribly wrong. That's terribly wrong, but we take advantage of the fact that you cannot have a cation without an anion. And so the cation entropy is terribly wrong. It's way too low. But that means the anion entropy is going to be way too high, and when you add up the cation and the anions, those errors cancel each other out. And so this is the same thing we're going to do here. The potential of an individual electrode is impossible to establish because we run into the difficulty of 2 unknowns. I mean, we could estimate it using quantum mechanics, right? But that's not so easy. And so maybe not impossible, but extremely difficult to establish with any sort of accuracy. So an arbitrary 0 is chosen, and what's our standard arbitrary 0? Hydrogen. And not just H plus in this case, it's going to be the standard hydrogen electrode. And we're going to see it's going to be both H plus and H2 in this case, or the SHE. So what is the standard hydrogen electrode? The standard hydrogen electrode looks like this. It's this, 2H plus. Actually, this is the reduction potential here. But the oxidation potential is the same. So if we look at the reduction potential, reduction is gain, 2H plus 2 electrons, this is an oxidizer, yields H2. We say that that reduction potential is 0. That is, it's not that H plus has 0 strength as an oxidizer, it's just arbitrarily selected as 0, or 0 point. The reverse reaction is the oxidation, and the oxidation is also going to be 0. And it's not because this is a bad reducing agent, it's a decent reducing agent. In fact, it's a very good reducing agent. It's just arbitrarily set at 0. And the way we set this up is like this. We bubble hydrogen gas in here. The hydrogen gas comes into contact with the platinum. And then we also have H plus in here. So let's see how this thing works. Platinum is used because it's unreactive metal. So Petrucci does this thing that's kind of funny. He uses the reduction potential for the cathode and the reduction potential for the anode, but reduction only occurs at the cathode. Oxidation occurs at the anode. We use standard conditions. The ionic species are 1 molar, the gases are 1 bar, or 1 atmosphere, approximately. We need some kind of, the electrodes have to supply the electrons. Hydrogen is not an electrical conductor, so this is why they use platinum. You use platinum, you either feed the electrons into that anode or cathode compartment, or remove the electrons from there. So, where no metal is indicated, we use some conductor, inert conductor like platinum, gold, whatever. So let's take a look at this reaction. This reaction, the way we're going to read this is like this. This is our electrode, platinum, because hydrogen is not an electrical conductor, nor is H+. Well, H+ AQ is, but we aren't going to be able to feed electrons. And so what's going to happen is the hydrogen gas, under standard conditions here, gets oxidized to H+ under standard conditions here. The electrons from this oxidation get fed into the platinum here. So the platinum takes electrons, excuse me, passes them through an external wire, external circuit, over to the cathode. At the cathode, well, copper can feed the electrons to the oxidizer. As copper feeds the electrons to the oxidizer, copper 2 gets reduced to copper metal. The cell potential here is 0.340 volts. Out of this 0.340 volts, how much is attributed to the anode and how much is attributed to cathode? We don't know, because this is x plus y equals 0.34 volts. So what we're going to do is we're going to set this one to 0. If this one gets set to 0, then that means the cell potential is all this. And so the way I would write it, which would be which would be a little bit different than Petrucci, is like this. So the the cell potential, this is all under standard conditions, so that's why I'm going to write that. And it's going to be at 298 Kelvin. Because the temperature is not stipulated in standard conditions, so we have to specify it. And so this is going to equal the anode potential plus the cathode potential. The anode potential is this. It's going to be H2 gas goes to H+. Okay, we don't care about the 2 here because the 2 is just a stoichiometric ratio. We care about the concentration here because the concentration has got to be 1 molar. It's under standard conditions. Plus the cathode. The cathode potential is copper 2+ goes to copper solid. That would be it. And so in other words, this is our oxidation potential. This is our reduction potential here. And what we're going to get is we arbitrarily assign this one 0 volts. It's defined as 0 volts. So that means that E0 for the copper 2+ copper solid potential is equal to 0.340 volts. Well, that's a big error. It's a big error, but that error cancels. And so we're okay. Okay, so let's take a look at how Petrucci sets this up. How Petrucci sets this up is it looks similar, E0 of the cathode minus E0 of the anode, but you have to be very careful here. You have to be very careful because Petrucci doesn't write something here. He has to write E0 of reduction for the cathode minus E0 of reduction for the anode. And so this is very tricky. So take a look at the couples. Copper 2 goes to copper. What is that? That's reduction. It's gaining electrons. Reduction is gain. Copper 2 gains electrons. H+ goes to H2. What is that? H+ goes to H2 is reduction. H+ is gaining electron. This is reduction plus reduction. Is that right? Well, no, it's not right but he has a negative sign there. And so that makes it okay. You know? I don't care which way you use, you know, but just be careful. I'd like you to use my way, because when you use Petrucci's way, the numbers lose their meaning. And so we get the same answer, Petrucci and I. This one's defined as 0 volts. You know, hydrogen either way, H2 or H+, whatever couple we're looking at, flip it, and we end up with this. So that's shown here. So what we do is over on the left we have the anode, over on the right we have the cathode, we have the oxidizer. The copper 2s are pulling the electrons, they aren't going to pull it off copper, they keep pulling. Eventually they're trying to pull it off the platinum, but they're going to be unsuccessful pulling it off the platinum. But if a molecule of hydrogen gas comes into contact with the platinum, then the hydrogen gas can lose the electrons to the platinum. Those electrons get fed over here, over the copper 2. When the hydrogen gas loses electrons, it makes H plus AQ. So that's what we're going to have. Now, we're going to call this side 0 volts. This side is going to be plus 0.34. Now, if we try to set up a cell, but in this case, over on the right, we put in zinc with Zn2+. What happens is the electrons start to flow backwards. In other words, what we have here is we just hooked up the voltmeter backwards, basically, because, and then we labeled this wrong, because normally we put the anode on the left, and in this case, it turns out zinc is a better reducer than hydrogen gas. And so zinc is going to be the reducing agent. And so over here, this is going to be the anode. We generate electrons and we let it flow here. We hooked up the voltmeter backwards because this should be plus 0.763 volts. But we are going to leave it as negative. The reason we're going to leave it as negative is we're going to pretend that the SHE, of the standard hydrogen electrode, is our anode. If we pretend that this is the anode, well, we see the electrons are flowing backwards here. If the electrons are flowing backwards here, then that tells us that the reduction potential, Zn2+, goes to zinc solid, is negative 0.763 volts. And so from something like this, we generate a table like this. The table is going to show all these are all reduction potentials here. Fluorine is going to have the highest reduction potential. A high reduction potential means it's got a high likelihood of being reduced. Fluorine is the most powerful oxidizing agent. It wants to take electrons to form fluoride. And so that's going to have the highest potential, plus 2.866 volts. If we look at H+, look at the reduction potential for H+, it's 0 volts. Does that mean H+ doesn't want any electrons? You know, reduction is gain of electrons. H+ doesn't want to gain any electrons? No, that's wrong. This is arbitrarily set at 0. And so this is why we have to be careful about what a negative sign means here. A negative sign, what this means here is not the electrons are going backwards, like we just saw. A negative sign here means that these are weaker than H+. And so lead 2, tin 2, iron 2, zinc 2, these are all weaker oxidizers than H+. H+ is given a value arbitrarily set to 0. And these are oxidizers that are stronger than H+. And so a positive reduction potential means it's a more powerful oxidizer than H+. A negative reduction potential means it's a weaker oxidizer than H+. But that negative doesn't mean it goes backwards. That negative doesn't mean it's an oxidizer instead. It just means it's weaker. The weakest oxidizer is lithium ion at negative 3 volts. Well, that's negative 3 volts weaker than H+. That's all that means. Well, let's do some more here really quick. And so if we take a look at this next cell here, this is going to be copper solid goes to copper 2 plus. Silver ions go to silver solid. Look at something like this. And this is what we have here. E naught of this cell is going to be equal to the copper solid. Sorry, that phone is buzzing. Copper 2 plus couple. In other words, this is the anode, or this is oxidation, plus E naught for a silver plus going to silver solid, which would be the cathode, which would be reduction. Now, silver plus going to silver solid is 0.800 volts. 0.800 volts. But there's something weird about this, because when I look at the reaction, this is copper solid plus 2 silver ions. Well, what about this 2? If I have a 2 here, don't I multiply this by 2 and make this 1.600 volts? And the answer is no, I don't do that here. The reason I don't do that is because this is just the stoichiometric ratio here. And so I would just need 2 moles of silver for every 1 mole of copper. But it isn't really going to tell me the pulling power. Another way of thinking about this is like this. Let me erase this here. The other way I can think about this is like this. These are under standard conditions here. And since they're under standard conditions, it would be like this. The stoichiometry of this says I need 2 silvers for every 1 copper. Well, what if I had 1 silver? So if I only had 1 silver, that would be like 1 gallon. If I had 1 gallon of 1 molar Ag plus versus 2 gallons of 1 molar Ag plus, is 2 gallons of 1 molar Ag plus twice as concentrated as 1 gallon? No. They have the same concentration. That means they're going to have the same pulling, the force. And so it's just that this is going to have twice as many ions. Well, that twice as many ions is going to result in twice as much reaction, which could result in twice as much energy. But other than that, it's going to have the same voltage. And so it's like this. You know, a D cell is a heck of a lot bigger than a C cell, which is a heck of a lot bigger than a double A, which is bigger than a triple A. So does that mean the D cell battery has the highest voltage and the triple A battery has the smallest voltage? Or do they all have the same voltage? Do you know the answer to that? So this is like having a D cell battery, and this is like having a double A battery. A double A battery is a heck of a lot smaller. Since it's a heck of a lot smaller, does it have a lower voltage or the same voltage? Did you know the voltage is exactly the same? The voltage is exactly the same because they're made of the same thing. Then what's the difference? If the voltage is the same, what's the difference? One has like 2 gallons worth of chemical and the other has 1 gallon's worth of chemical. If you have 2 gallons worth of chemical, you're going to have a longer lasting battery, but the voltage will be the same because the ingredients are the same here. In other words, the reactants are the same. And so since the concentrations aren't different here, it's going to have the same kind of pulling power, except this one's going to have more energy stored in there than that. And so even though we have 2 here, this is just a stoichiometric ratio. We don't multiply the voltage by 2 here. But we would multiply, the energies, like delta H, we'd multiply by 2. Delta G, we'd multiply by 2. But E of the cell, we don't multiply by 2. We just leave it at 0.800. And then we look at copper, copper 2 plus. Well, when I look at copper, well, I have copper 2 plus goes to copper. Well, if I have copper 2 plus goes to copper, that's 0.34. But I'm looking at the reverse. I'm looking at copper goes to copper 2 plus. So I'm going from copper to copper 2 plus. If I reverse this reaction, I change the sign here. And so the copper 2 plus couple is going to be negative 0.340 volts. And so when I add up these two to get the cell voltage is equal to the anode potential plus the cathode potential. And so that's going to be negative 0.340 volts plus 0.800 volts, which is going to give me 0.460 volts. And so the way we say this is like this. The higher the potential, the more likely it is to occur. And so the strongest oxidizer is fluorine with a potential of 2.688 volts. Or 668 volts. No, 2.866 volts. The strongest reducer is lithium. Now, lithium is the reverse. So I have lithium going to lithium plus. The strongest reducer is lithium. Lithium's voltage, well, we have to change the sign. And so the strongest reducer is lithium with an oxidation potential of plus 3 volts. And so it's consistent in terms of the higher the voltage, the higher the potential. Now, finish. This. Here, now if we look at this, if we think about electrical work, you know, how much work you have to do in pushing electrons through an external circuit, it depends on how many moles of electrons you're pushing. So Z is the moles of electrons. And it depends on how much force you're pushing. Okay, and so the moles of electrons are going to be represented by how much charge you're pushing through the circuit. When we take this, and so the work of electricity is just going to equal minus Z. Z is the moles of electrons. F. F is called the Faraday constant, after Michael Faraday over there. And the Faraday constant just tells us that there are 96,485 coulombs on a mole of electrons. And so the moles of electrons cancel. That leaves us out of how many coulombs worth of charge we're pushing. An electron's like 10 to the minus 18, I think, or 10 to the minus 19 coulombs per electron. So that's a lot of electrons. Times the potential, that is how much force, the cell potential you're pushing through there. Well, that's the work. And where does that energy come from for the work? That energy is going to come from the driving force for this chemical reaction, delta G naught. In fact, delta G is called the free energy, and the origin of free energy comes from the energy that's available to do work. And so delta G naught will be the energy that's available to push the electrons through that external circuit. And so under standard conditions, this is equal to ZF E naught of the cell. So there's a weird thing that happens. The weird thing that happens is this. Let's say we're interested in this reduction potential here. We want to reduce iron 3 all the way to iron metal. Well, that's going to take iron 3 plus 3 electrons goes to iron metal. So what is the reduction potential for this? Is a question mark. When I look at appendix D, I have the reduction potential for iron 2. So iron 2 plus 2 electrons goes to iron metal. That is minus 0.440 volts. And then I have iron 3 plus 1 electron goes to iron 2. That's plus 0.771 volts. Now the minus and the plus are relative to H plus. So this means that iron 2 is a weaker oxidizer than H plus, whereas iron 3 is a stronger oxidizer than H plus. And so if I add up these two reactions, can I just add up the cell potential, the half cell potentials, or the reduction potentials here? It turns out I cannot add these together. And it's because that these reduction potentials are what we call intensive, not extensive properties. And so we can't just add these and get a voltage. If we add them, we get a voltage of 0.331 volts. Well, that's wrong. But we can add the delta G's, because the delta G's are going to depend on how much, you know? If you have 1 mole of 1 molar iron 2 plus versus 2 moles of 1 molar iron 2 plus, then that's going to change how much energy we have. But if we have 1 mole of iron 2, 1 molar iron 2 plus versus 2 moles of 1 molar iron 2 plus, then that's not going to change the voltage here. That's like 1 gallon versus 2 gallons. And so over here, we can add these. Energies are extensive. We could add delta H's, we could add delta G's, but these reduction potentials and oxidation potentials aren't extensive. We can't add them together like we'd like to. And so this we can't do. This we can do. Well, once we get this, then we can calculate what E naught of the cell is we could just use this equation to just solve for E naught of the cell. And so if I want to determine that, I'd add up the delta G's and then just calculate E naught of the cell is equal to delta G naught minus delta G naught over ZF. Okay, what are the units of this? Well, the units here are going to be coulombs times volts. A coulomb times a volt is a joule. And so over here we're going to get joules. Normally this is in kilojoules, but we do joules divided by ZF. ZF would be coulombs. A joule divided by a coulomb is equal to a volt. And so that would be the units here. This would be the units here. So we calculate our delta G value here, 0.109 volt, 0.109, this is weird. This should be 0.109 joules, right? Actually, this is wrong. Something wrong with this number. Yeah, this is the wrong number. Well, anyway, we get this delta G value, and then we solve for E naught of the cell, and we get this. This looks like the right number. Maybe. Double check the calculation. All right, I'm going to stop here. So we did the first, 2 sections of chapter 20. And let's take a look at this. I posted the old chapter 20 exam on Piazza earlier today. Unfortunately, we aren't going to have time for a chapter 20 test. So what I'm going to do is I'm going to incorporate a few more chapter 20 problems into the final exam. You know, the final exam is still going to be cumulative. The final exam is going to be multiple choice. You know, the final exam is going to have about 60 multiple choice questions in less than 3 hours. And so you're not going to have more than 3 minutes per question. And in fact, I'm going to give some extra bonus chemical reaction ones, so you probably don't want to spend more than 2 minutes per multiple choice question. And so let's see how much of this test we can do now. You should be able to do numbers 1 through 7 here, and some more, like 17 and some others. And so let's take a look at 1 through 3 first. This is hard to read, I'll blow it up. And so take a look at this, and then I'll give you a few minutes to do these.